Hi, I'm Kirsch. In this video, we'll be showing the startup and steady state and step response behavior of a flyback converter using PSpice. We'll also be looking at the waveforms. This is a 5-volt 2-amp flyback using the LM5156 control chip from Texas Instruments. If you've ever had a power supply that simulates and comes up slow, it overshoots by too much, or it never settles at the appropriate output voltage, this video will show you what to look for and why those happen. So quick housekeeping, make sure that if you open up OrCAD, you're using the Allegro X license so it matches what I have on the screen. The project is already wired up. This takes in 9 to 36 volts on the input side. It serves a load at 5 volts, 2 amps. The transformer ratio and also the feedback ratio is tuned so that when you get 5 volts on the output, you also get around 1 volt on the feedback node. So what's on the agenda for this video? Well, number one, I'm going to show you what are the ideal set of conditions and techniques you can do to help you simulate your flyback converter and power switching converters in general more easily. Number two is I'll show you the SPICE settings you should put in your own circuit simulation demos so you can get this thing to converge and also to speed up simulation. Finally, you'll understand some of the flyback converter's behavior and what to look out for so that it settles at the right voltage that you're expecting and behaves correctly. These are techniques and best practices you can take to any power switching converter topology. So let's get started so you can start simulating these boards. So the first way I optimize for circuit simulation in PSpice is to use non-ideal models for devices. Let me give you an example. Here, this power supply, right? Instead of using pulse to represent a ramped voltage supply on the input voltage, because that mimics reality. It also helps the solver solve things more easily. Next, I have a non-ideal capacitor. Using non-ideal components that have real initial conditions for voltage, real tolerances, equivalent series resistance, just like any real capacitor would, those really help the solver for your circuit simulate more easily, less stress, and not as stiff matrices for your solutions. Another thing is adding parasitic capacitance and any equivalent inductances where you can, right? And where it makes sense. So this transformer has some parasitic capacitances around here to make it easier for the solver to solve for the transformer and simulation behavior. And if you're wondering how I do this non-ideal component stuff, I use the PSpice modeling app. See here, it allows me to set specific things for my flyback converter and my capacitor. And finally, of course, I use the actual SPICE model for the manufacturer chip. For instance, I have this TI LM5156 chip, and if I right click on it, I can edit the SPICE model to match what's going on with the datasheet. So yeah, use non-ideal devices, add parasitic capacitances, use real SPICE models for your chips, and that'll help any switch mode power supply or any circuit when it comes to simulation. So that's number one. Now, while setting up a non-ideal circuit with these parasitic capacitances and everything will help your circuit, sometimes it just won't converge because it's too complex, or even if it does converge, it takes a really long time. This is where I'm going to explain the SPICE settings you'll need to use to increase the speed of your simulations or just get them to converge in the first place without having to use auto converge. All right, so let's jump into the settings. I'm going to go into my PSpice simulation profile. Then under analysis for transient, I'll set my runtime to 12 milliseconds, and I've set my maximum step size to be a fraction of the runtime. Usually you want it to be no greater than 2 or 3 orders of magnitude less than your runtime. So I set mine to 50 nanoseconds, could be 80 nanoseconds. More details are in the design guide. I also make sure in my configuration files that in my library, I've added the .lib files to my configured files, my list of configured files. Also, make sure your .lib files are in the same directory as your project, just to be safe. Sometimes it'll get confused if they're not. Under my options, this is what requires a good bit of changes and massaging. For speed, you can change your simulation speed from your default 3 to something like 5 to up the speed of the simulation. Relative tolerance, instead of the default 0.001, set it to something a bit higher, like 0.03. Some of these don't need to be as strict. My voltage tolerance, or best accuracy, and absolute tolerance, we don't need microsecond or picosecond level tolerances for a lot of these circuits. Charge tolerance, I'll keep the same because sometimes you do need that to be what it is at the default. Same for Gmin. I used to modify and change Gmin. You don't have to, because depending on your SPICE model for your chip, having Gmin larger than your 1 to the E-12 could cause issues for calculation. So you're going to leave that at default. And this refers to the minimum conductance of any branch. You're going to want to understand and have the solver see those minimum conductances in any traces. That's the inverse to resistance. So conductance is in Siemens. Right. So now that we have the conductance at the appropriate value, now you could do this as 1e to the -9. That is a common tactic that people use to make simulation converge and make it easier, but not always. You don't have to in this case. For your iteration limits, this is the DC unbiased blind iteration method limit, meaning it's going to stop after so many iterations of trying to solve or backstep to solve something. You can increase this to say 300, 400, 500, but that won't necessarily help your simulation. It can, but not always. Then you have your transient time point iteration limit. Same story essentially for ITL4. Just because you increase it doesn't mean it's going to necessarily fix or change anything. But it does give this solver more tries or opportunities to do some solving for you. Sometimes you just need to increase the limits and it'll work out. Other times, not the case. DC and bias best guess iteration limit. This is typically in case you can't find a DC bias for the circuit. Usually though, when that happens, the circuit has some issue in the design itself. So you're going to want to look at it, because in most cases, if your circuit is designed properly, you should be able to find a bias point, or the algorithm should be able to find a bias point. Then you have TNOM. The rest of these settings you can keep the same. Check mark by default adv conv adv conv, right? That does not necessarily mean that you turn on auto converge though. Leave that unchecked. Why? Because there could be a conflicting setting in your general settings if you change those before you change auto converge. So you may want to switch back to your default settings instead of before setting auto converge, because it messes with some of these things. Another set of settings is under analog advanced. Set the worst case deviation from 0 to 1. Gives you a little bit of room there for your worst case deviation. Sometimes that's needed when dealing with hard switching state converters. The more you have non-ideal components and circuitry in your circuit though, the less you'll need to use that or any of this. Under bias point, we have our default settings. Those are fine, but click under here, transient. Now this is very important. By default, you're going to see a default solution, right? Your integration method. But change this to gear. The gear integration method has its own benefits. Typically, you want to go with gear for switch mode power supplies. The relative time step tolerance can be changed from 7 down to 5. You can also play with things like using C-shunts for non-idealities in circuitry. I just manually and physically put the capacitors in there. The biggest drag on performance that I've noticed is the amount of data you collect and also file size. So if you go to data collection, this is my hack for much faster simulations. Turn all of these off. Voltages, current, power, digital, noise. You don't need all that a lot of the times. You can select your option and turn it to none. Well, not all off, but you can turn this to at markers only. For voltages, you typically want to use your probes to jump around it at any time. So I put this at all but internal circuits for voltages, so I can move my probes around. For current, there are usually only 2 or 3 spots or devices where you want to always measure the current. So I put that at markers only and preload my markers. For power, all but internal circuits is what I use because I want to be able to check my components for their power consumption when I'm doing component selection. Digital, don't need it. Noise, unless you're doing noise issues or whatever, noise analysis. All right. So that is the full setup. It's a lot of settings. For more details, you can check our design guide. But yeah, use these settings and see how your simulations significantly increase. Right, so use those simulation settings and your circuits, especially power switching converters, will simulate way faster under some of the most stressful conditions. All right, so we've got a few things going on here. The first is the V out. Is it behaving correctly? So if we look at the V out, I'm going to thicken this trace. So we right click, choose trace property, and change the width to something we can actually see. All right. In the trace, we see that the V out goes up to 5 volts. And then around the 6 millisecond mark, it droops down and goes to tries to get back up to 5 volts. This tells me that it's not quite as stable as I'd like it to be, but it does attempt to get back to that with such a load step change. So why did it suddenly droop? It's because of this current. I set the current to turn on and draw 2 amps. That's full load for 5 volts, right? And the fact that it doesn't quite recover fully to the 5 volts tells me that there is some stability issue a little bit. So it seems fine. Before I go into current, I want to talk about the startup. If your circuit is taking extremely long to even get to V out, it could be the length of time of your soft start. For most chips or a lot of chips, you can have internal soft start or external soft start. I went with an external soft start option, so that's SS turned to 0, and I placed my own capacitor to control how quickly the controller is allowed to start. I sized it at 220 nanofarad. If you want it to start a lot more quickly, then you can drop that down to say 22 nanofarad. Read the data sheet for the device so that you know what's going to give you an amount of soft start. Soft start basically keeps it in a soft starting state so it doesn't just shoot up and turn on all of a sudden when you have a load attached to the output of this V out here. If it's taking forever for your voltage to get to its level, like its starting phase, then you want to decrease your capacitor on soft start so that the circuit starts more quickly. So I put my soft start somewhere where, see this voltage, it could start to ramp up and then finally break out and go toward its 5 volt output. Somewhere around the 3 to 4, somewhere around the 1.5 to 2 millisecond mark. Okay. Once soft start has done its thing, then our voltage goes up. Another problem is when you have your output voltage starting, ramping up, and settling, but it doesn't ever quite reach the voltage you were hoping for. There are 2 reasons for that a lot of times. One is the windings of the transformer. You're going to want to change that. Or if it's not the windings of the transformer, which is causing you to saturate or to go over limit on your duty cycle. Usually you don't want your duty cycle more than 50% for a flyback converter. If it's not that, like stressing the circuit to hit its max duty cycle, then it could be your output voltage divider. So let me show you what I'm talking about in the circuit. So when I was having issues with the V out not hitting my 5 volts, it could only stay stuck at 4 volts. I checked that the transformer windings were exactly what they needed to be. Why? Because if the windings kick too much responsibility, so to speak, or energy to the primary side or to the secondary side, particularly the primary side, then that means my duty cycle could only get to a maximum amount of duty cycle, say 47%, 50%, which would limit the amount of energy you can release, dump into the transformer, and then release once once the switch is turned off. Most likely, though, it's the sizing of this output resistors, right? This feedback. So I changed it to where it's 30K with a 7.5 kilo ohm resistance. The design formula for that is in the design guide. So once you size this correctly, and once I did that, it behaved well at 5 volts. So just 2 things to check whenever your output voltage doesn't quite, like it settles and everything works, but it doesn't quite hit the voltage you need it to be no matter what you do. All right, we have looked at all of the most important different knobs or settings, so to speak, and things to look in your circuit for all of the common issues you'll find in a flyback. Well, not all of them. So if you want the rest of this information, check out the design guide, download that, and you'll get more of the details so you become very aware of the things you need to look for and change in your flyback converter. Hope this helps with your simulation settings, getting your simulations to run, regardless of your power electronic or switch mode power supply. All right, until next time, this is Kirsch, and have a good one.